Check, check. Check, check. Hello, people of TikTok. How's everyone doing? Happy Friday. I think everyone can see me now. I'm just making sure everything's working on my end. How's everyone doing? Just had a phenomenal lunch. Got a vegan sandwich from Whole Foods, and then it was kind of nice today. Was able to go to a coffee shop and just enjoy, the environment, I would say. Hope everyone's Friday is going well. Today is off trail. First of all, I just want to say that I'm sorry for not joining on Thursday. Thursday was a little, well, I guess yesterday, was a little busy, so I had to meet with a few students, so I couldn't really get on live, but I'm really bummed about that. But I think we're going to cover some of the material today. We are going to do some partial derivatives, and then we're going to combine that with implicit differentiation. But today's off trail. We're going to do whatever you guys feel like. So if you see in the comments, if you feel like you wanted to cover something specific, I mean, I can definitely do that, but I'm just going to go ahead and get started on a specific derivative or integral that I posted on a TikTok yesterday, and it involves the Feynman technique. I don't know if you guys have heard about that, but I know that was heavily requested, so I'm going to go ahead and show that really quick. And it's a little difficult, but again, today is just off trail. All right. We don't really care about what we're doing. This is just anything goes today. We are going to try to do as many problems as we can using whatever methods we like. We're just trying to have some fun here. So the integral that I had posted on my video yesterday looked like this. It was the integral from 0 to 1 of x squared plus 1 over natural log of x dx. And a lot of people had some ideas on how they wanted to solve this. And a lot of people posted some comments on what they wanted to do, and they wanted to try integration by parts. Fuzzy Balls, what's up? Ramajan Sums. Oh, okay, so I'm Burner, I'm hearing Feynman. Okay, maybe we can cover that. To be honest, don't think I've covered that in a while, but I'll look it up. Maybe we can do it together. Okay. So someone was mentioning the Feynman integral or the Feynman technique. That's exactly what we are going to do here. So how does it work? I've been trying to look at a lot of videos and a lot of websites explaining how this is done. And ultimately people just go, yeah, you just take the integral and you kind of just solve it and you're good to go. So I'm going to try my best to show you how we go ahead and integrate this. So we're going to start off by creating an equation. Some people use alpha, but I'm just going to use k. So we can definitely visualize the difference here. Okay, so I'm going to go ahead and recreate this and look at what I'm going to change. Instead of the power of 2, I'm going to change that to a k plus 1 over natural log of x dx. Yes, I agree. The websites are kind of interesting. It's one of those things that when you start, the people who do explain it are just incredibly smart, incredibly gifted, and it's kind of difficult for everyone to keep up. So you kind of have to just, try your best to solve it yourself. So that's what I've been trying to do for the past few nights, and it's driving me crazy. There's some examples that I just cannot solve, but this is the best one that I felt super confident about. So I'm definitely going to cover this one. Okay, so again, if you notice, I just created a function in terms of k, and all I changed was the power of 2 into a k. And now what we're going to do is we're going to take the derivative of this function. Now, the derivative of this function, if you look on the left side, this is the derivative in terms of k. So on the left side, what we're really doing is we're taking the partial derivative in terms of k. And a lot of people are probably not going to quite understand what partial derivatives are, but we could definitely review that after this, and we can talk about how that can relate to implicit differentiation. Okay. At dog, someone said integration by parts. Trust me, integration by parts will not work here, but let's continue. Okay, so I'm going to take the partial derivative. Now, the way the partial derivative works, okay, is you got to treat every variable but the k as a constant. And that's one of the neat things that Richard Feynman came up with, and it's one of the neat things about this specific integral. This natural log of x is just an x, so technically we're going to treat that like a constant. So before I even take my derivative, I'm going to pull that on the outside. Again, don't worry about the notation. I mean, I know it's a little tricky, but we'll talk about why I'm doing this. All right, so now I'm going to be able to take the derivative of this x to the power of k plus 1. Now, before I take the derivative, or the partial derivative, let me remind you of the basic exponential function. So if I have d over d to the u of any value to the power of u, that's equal to a to the u natural log of a. So that's exactly what we're going to do here. Okay, I have 1 over ln of x, integral from 0 to 1 of this partial derivative. This is the tricky part. I need to take the derivative of x to the power of k, but I'm taking the derivative in terms of k, so this is going to become x to the power of k times natural log of x dx. Again, I just took the partial derivative. Okay, so Frog King, yes, you're in Calc AB. I'm doing something called a Feynman technique, something you won't ever learn. Or not you won't ever, I'm sorry about that. Something you won't learn for a while. This is called the partial derivative, and I'll explain that later on. I feel like we really need to do some partial derivatives in a second. Okay, you guys, you're going to see why I'm doing this. Again, I took the partial derivative. This is off-trail math, Friday, anything goes. So we're just kind of learning some new techniques here. But you're going to see why I'm doing this. All right, now let's go ahead and bring the 1 over natural log of x back inside. And let's make it 0 to 1, x to the power of k natural log of x over natural log of x dx. And this is the cool part about the Feynman integral. We are going to be able to cancel out the natural log of x. And look what I have now. I have the integral from 0 to 1 of x to the k dx. And don't forget, this is equal to the derivative of f in terms of k. All right, we just started, and we're already making things sort of smaller here. So let me go ahead and make some space on the blackboard. And again, this is what we call the Feynman technique. It's not supposed to be something that we learn in Calc A or Calc 1 or Calc 2. It's technically like more higher level math, but I just wanted to introduce this. Okay, so now we're going to go back, and we still need to integrate this value on the right side. This is the integral from 0 to 1 of x to the power of k. And now we're going to actually use, we're going to integrate this in terms of k. So we're just going to use the power rule. This is going to be x to the k plus 1 over k plus 1, and we have our parameters 0 to 1. And we're using the first fundamental theorem, and we're plugging in the 1, and then we're going to plug in the 0. So how does that look? This is 1 to the power of k plus 1 over k plus 1 minus 0 to the power of k plus 1 over k plus 1. Now, let me know in the chat, what is this value that I circled in red equal to? Can anyone tell me what that value that I circled, what is that equal to? 0 to the power of k plus 1 over k plus 1. Thank you. Yes, I see a bunch of zeros. That is 100% correct. So now what we have is f prime of k is equal to 1 to the power of k plus 1 is just 1 over k plus 1. Look at that. And now we just have an equation in terms of k. That's what this is what the Feynman technique does. It gets rid of a lot of things, and it creates the equation in terms of another variable, in this case k. All right. Let me rewrite the left side. It's f prime of k. I think, who was this? Was this Newton that created this notation, or was it Leibniz? I don't remember, but I'm going to change it to the other one. Notice that I simply just rewrote the derivative on the left side. Okay? So now what I'm going to do is I'm going to use separation of variables and multiply the dk to the other side, so that I have df is equal to 1 over k plus 1 dk. Got it. So Leibniz did the notation. Okay. Yep. Yeah, I always forget the two. And so now we're going to be able to integrate. And look what that gives us. That gives us a nice function f in terms of k is equal to, if we use substitution for this, this just becomes natural log of k plus 1. And technically there's a plus c. Okay, I posted a video this morning, and I just say you can completely disregard it. Some people will argue why we can get rid of it. But the main reason why we can get rid of it is It's up on the top, but for now, let's just forget about it, okay? Just bear with me. We're going to assume that this is c is equal to 0, and we're just going to leave it as natural log of k plus 1. Okay, now let me make some space on the blackboard here. Keep in mind, this is f of k. Okay, so remember, we said f of k was equal to this natural log of k plus 1. But this was also equal to the integral that we created, 0 to 1 of x to the power of k plus 1 over natural log of x. And since in the very beginning I asked to find the integral from 0 to 1 of x squared plus 1 over natural log of x, the only difference from this integral and the one that we have was that the k value is 2. But we already know what that is equal to. Let me circle it in green. We already know that that's equal to ln of k plus 1. And so all we have to say now, this is equal to ln of absolute value of our value k, which is 2 plus 1. So this entire integral is equal to natural log of 3. No, this is not calculus 2. This is beyond calculus 3, I would say. Technically, you are doing, it's more calculus 3, but it's just a different technique that I think it's very complicated, okay? You definitely don't need, yeah, you're right, Burner. I don't need the absolute value. I can definitely get rid of it, but I'm just going to keep it as natural log of absolute value 3. Yes, because it's just 3. But to make everyone happy, I'll just do natural log of 3. So one of the cool things about this, let me just erase my work. I can now give you 0 to 1 of x to the power of, 4, for example, of this function, and we know that this is going to be natural log of the 4 plus 1, so this is natural log of 5. So again, this is what we call the Feynman technique. I'll spell it for you guys. You guys can look it up, Google it. It is so interesting, or like I would say a little difficult. Very beautiful technique, but very difficult to understand. This is one of the easiest examples that I've seen. And it gets extremely complicated, okay? So I'll try to do some more of these because I think they're so fun, and I've been trying my best to try to do a lot of these problems, but I just can't. I mean, it gets insane, all right? Okay, someone said you can also solve via non-elementary functions, but you learn in a complex reanalysis. Yes, absolutely. Maybe that's something we could do another time. I have to look at that. So many people have been commenting about complex analysis in my my profile, in my videos, and I definitely have to revisit it. Yeah, thank you, Burner. Yeah, it's difficult, man. So intense, and I think it's in the writings or in like the papers that people post online. I mean, it's just as simple as like, well, you just kind of integrate it and then you're good to go. I think it needs more explanation, and I think it's worth looking at. Oh, x to the power of 4 minus 1. I think you're right. But you know what? The cool thing is that if it was minus 1 or plus 1, I think we will still arrive at the same answer. But you're right. I think it should be integral from 0 to 1 of... Actually, no. I think I wrote it as plus 1. But either way, I believe this will still give you the same answer. Okay. And so here's the thing. I was super looking forward to the Feynman technique, and I felt super confident with doing that. And I try to integrate it or use that technique using this equation here, or this integral. Didn't work out. I tried it, and it's so difficult. Okay. Differential equations. So what specifically using the series solution? There's a lot that we can do. I mean, to start off, we could even just, mention, or we can talk about Maclaurin series or Taylor series. That's one thing for sure. I wanted to move on to explaining partial derivatives and implicit differentiation, but does someone have a specific integral that we'd like to solve, or is there a specific problem just in general that we'd like to solve? Let me know in the chat if you guys have something in mind that you definitely, or a specific equation you guys wanted to do. I wouldn't say this is necessarily calculus 2, Popsky-Plesto. So 2 plus 2, yeah, we could definitely do a 2 plus 2 integral. You know what? let's just move forward and let's talk about different implicit differentiation, and then I'll talk about the other ones. So yeah, it's popsicle. Go ahead and send me, if you go to my profile, you can email me there, and then we can I'll try to open it up. And Tyler, the same thing. So try to send that integral to my email. I will pop it up and then come back on the channel and let me know how you did that. Okay. Here's the thing, Rishi, the integral of 1 to pi over 3 of cosine of x, I don't know how to do. I try to use the Feynman technique and it just doesn't work for me. Someone said integration by parts, but we can try that and it just didn't work for me. Let's try it out. You know what, guys? Today's Friday. We're doing whatever is on our mind. We're just trying whatever method. Let me show you why integration by parts wouldn't work in this case. Okay? Because if you tried integration by parts, what should we make our u equal to? Perhaps cosine. And then so du is negative sine of x dx. And then we have dv is equal to 1 over x dx. So that means that our v is equal to natural log of x dx, or just natural log of x. Okay. So would that even work? What do you guys think? Let me just write it out. Oh, I'm just gonna call you Popsicle. Popsicle. I see the equation. I'll write it out in a second, and we'll do that together. Okay. So with this specific problem, someone said integration by parts. Yeah. See the non-elementary function. Mm-hmm. Yeah. And see, I have to definitely look into that. I haven't seen that in years. It's been, I would say, almost 10 years since I've seen those functions. So I wouldn't worry. I'm not going to try to do that today, but I will eventually. You guys are really testing me. I mean, I am going online and I'm reading these things and I'm trying to look back at my previous math books, because there's a lot of material that people bring up all the time. But anyway, back to this. I just want to set this up real quick, and then I'm going to do Popsicle's problem. If we do U sub or integration by parts here, it's going to be UV, the ultraviolet voodoo. So it's going to be natural log of x cosine of x minus integral of natural log of x and then times negative sine of x dx. And you see how complicated that would be? It just wouldn't work. Okay, v, I believe, is my, in terms of the DI method, the v is my I, or part of the part that I integrate. Okay. Let me go back to Popsicle's problem, because I know he requested it, or they requested it. Okay, if I believe, we can talk about this problem later. We can discuss it, and we'll do it in more detail if you guys like. But I just want to do this integral that Popsicle requested. It was x cubed plus x plus 1 over x. Is that correct? Popsicle, let me know if that's correct or not. Okay, cool. Pretty simple, and I would say a lot of the people on the chat here would definitely try to confirm how you would do this. Fuzzy Ball said long division. Okay, Bernard, I'll see you in a bit. Okay, so we're just going to split this. Notice that we only have one term in the denominator. We can split this up to look like this. Okay, you would definitely split this up. Because everything has one denominator, we can just split it up so it has into the sum of multiple values with that same denominator. And now we can go ahead and simplify this. The first term, x cubed over x, is just x squared, plus the second term, which is just 1, and then plus 1 over x dx. And now if we wanted to do, go even further and really show every single step, you're technically integrating this separately. So I'm just going to show you the integral here, because we can split the integrals up if they're adding or subtracting. And now we just use simple integration problems. So the first one is just x cubed over 3 plus the second problem, which is going to be x, plus the last one. If you recall, or if you haven't covered this, this is a very special integral, and that's just the natural log of absolute value of x. And are we done, or did we forget something? Definitely forgot my plus C. Okay, user, user 20179. Just go ahead and practice. Practice as much as you can. Okay. Hi said integrate x squared plus 1 over tan x. I have a feeling that's not as easy as we think. Okay, does anyone have any suggestions? I don't even know what to do that. Popsicle, thank you for the rose. Thank you so much. All right, guys, looking at this problem, what do we suggest? I don't know. What are we thinking? I wouldn't know how to solve this. At least I don't think so. It's not integration by parts. At least I don't think it is. It's not use substitution. Anyone else have some ideas? Popsicle, the rose, thank you again. All right, if you guys have any ideas on how to solve this one, I wouldn't tell you. Okay, so Fuzzy Ball said trick sub. Should we try that? Yeah, let's try trick sub. Okay. I don't know if that's going to be correct. Who recommended this? Hi. Okay. Hi, do you know the answer? If you do, let me know. Otherwise, I think you're just messing with us. Okay, integrate x time. Okay, I'll talk about that in a second. I'll write that one down, Alexander. Okay, but let's try this one. Okay. So, someone said integration. Oh, I think I know what you're talking about. So you're saying, wait a minute, guys. Someone talked about, I can't even describe a Weierstrass sub. Let's look it up real quick. Hold on. Function, and I think we're looking for tangent, right? Or for one of those. Whoops. It's not this one. Can someone tell me which one we use? No. We're not using Wolfram. Okay, half angle. This is going to lead us to the half. We're going to talk about the integral of secant, because I think that's going to be extra useful. Let's see. I don't see it. Tony, what do you think? If we use that, would that even be possible? The Weierstrass sub? What do you guys think? Oh, see, Wolfram gives an answer. Yes, but do we know the answer to it? It's gotta be something. Okay. So I think it leads to something. Let's circle back on this one in a second. That one, x squared plus tangent of x, because do we know anything? I guess the only thing that I can see if we're looking at these functions, let me just write them down real quick, that tan of x is equal to sine of x over cosine of x, which is equal to 2t over 1 plus t squared over 1 minus t squared over 1 plus t squared. Okay. So let's go back over here. This is what I'm getting. See, can we use the Feynman technique? If that's the case, what would it be? So this is what I did. Using that Weierstrass, or whatever you want to call it, that sub, that's what we will use. And this will make your tangent equal to 2t over 1 plus t squared. So going to our integral, that becomes 1 integral of x squared plus 1 over, and then it's going to be 2t over 1 plus t squared well, we still have dx. So we definitely have to fix that. Do you guys see where I'm headed? Let me rewrite that. That's 1 plus t squared over 2t times x squared plus 1 dt, but we still need or dx, I'm sorry, not dt. You guys see how complicated that will get? Yeah, because if no one has an idea of how we can solve this, then we're just going to kind of abandon it from now. And then we're going to do a problem that Alexander mentioned. But I am going to use this particular method to talk about the integral of secant. That one, I guarantee that I do know. Okay? Okay. So let's try the integral that Alexander requested, and then I'm going to go back to a problem that's very similar to this, but for secant, okay? So let's do this one. And complicated, I don't know if we can use a Feynman technique. I wish I could, to be honest with you. We just did a Feynman technique problem. Okay, let's do this one real quick. So Alexander did this one. Alexander requested this, and then we will talk about some other problems real quick. Okay, so you said x and then times x squared plus 25 to the power of 1/2 dx. All right, guys, what do we think? What do we think, chat? What should our u value be? I'm definitely seeing a u substitution problem here. This is going to be a u is equal to x squared plus 25. So du is equal to 2x dx. And I personally like to move or divide the 2x to the other side so that I get du over 2x is equal to dx. And look what that's going to happen, or look what's going to happen here to our integral. We're going to have integral of x, and then we have u to the power of 1/2 times du over 2x. And look at the x's, they cancel out. So now I have 1/2. Let me just erase this. Let me just use yellow here. So let's do 1/2 integral of u to the 1/2 du. And now I have 1/2 times, I'm just going to use the power rule. Nice. So u to the power of 3/2 over 3/2. Now, people get confused a lot here when it comes to dividing by fractions for whatever reason. But what this really means is 1/2 times the reciprocal of the 3/2, which is 2/3, u to the 1/2. And look at the 2's, they cancel out. So now I have 1/3 u to the 1/2. And now I'm going to rewrite this. I'm going to plug in the value of u back in. So I have 1/3 x squared plus 25. I realized that instead of 1/2, it should have been 3/2. My bad, guys. My bad. Okay. And then obviously, don't forget your plus c. Okay, Luke, you said by inspection. I'm hoping that's u substitution, right? Okay, so a definite integration by parts problem. I mean, you can do so many definite integration by parts problem. Let's go ahead and do something like x squared sine of x. No, let's just do x, sine of x. And then this is going to be from 0 to 3 pi over 4. Okay. So let's see, guys. If we're doing a definite integral here, what should we do? I believe it was user 2179 said that they want to do integration by parts. So we're definitely going to do integration by parts. Now, the way I do integration by parts is I use this equation. Some people use that d. Okay, math nerd, you should definitely try to send me that answer. Okay, try to email me. Go to my profile, and you guys can send me that stuff. Yes. Okay, so it looks like dvr. Okay, so we're finding our values. Let's see. U is equal to x. Du is equal to dx. dv is equal to sine of x dx. And then v is equal to negative cosine x. Okay, who got that? It was you. Yes, perfect. Okay, now we're going to go ahead and plug everything in. So now we have x, or negative x cosine of x. All I did was multiply the u and the v, minus integral of negative cosine of x dx. And let's just fix a couple things here. This minus and the minus turns into a plus. So I have negative x cosine of x plus integral of cosine of x dx. And don't forget, we're not going to forget about the parameters yet. First, we're going to integrate the last part, and then we're going to put our parameters. And our last part is to integrate that cosine, and that becomes plus sine of x. And look, now we have our 0 and our 3 pi over 4 for our parameters there. Okay, so we're going to bring the 3/4 to all terms here. And that's negative 3/4 or 3 pi over 4 cosine of 3 pi over 4 plus sine of 3 pi over 4. And then we still have minus, and then we have to plug in the zeros into everything. And that's just going to be all zeros, but I'm just going to show you why. Because we have negative 0 times cosine of 0. That just cancels out. Plus sine of 0. And that just cancels out. So then our final answer is negative 3/4, or 3 pi over 4 times cosine of 3 pi over 4 is negative root 2 over 2 plus root 2 over 2 is equal to, and this is going to be positive 3 pi root 2 over 8 plus root 2 over 2. That is our definite integral. Nice, David. Yes. Not a problem. Okay. That kind of reminds me, I don't know. Should we continue doing integrals? Do you guys want to do derivatives, or do you guys want to do, here, I'll leave you with this one. Let's see. Best way to remember the unit circle is to do it one quadrant at a time. Okay, so I will learn the first quadrant, try to memorize the 30, 60, or the 30, 45, 60, 90, and just try to memorize the points. The way I remember them, and I just know that everything in terms of pi over 4 is root 2 over 2, and then when it comes to like pi over 6, it always starts with root 2 over 2 comma 1/2, and then if it's pi over 3, it starts with 1/2 comma root 3 over 2. To be honest, the way I did it is I would literally get a whiteboard, and I would just draw up every single point. And I will time myself. And I will say, okay, this is 30 degrees, or this is pi over 6, and this is root 3 over 2, comma 1/2. Okay, this is 45 degrees, this is pi over 4, and then this is root 2 over 2, comma root 2 over 2. Okay, this is 60 degrees, meaning pi over 3, and this is 1/2, comma root 3 over 2, and so on. And I will continue doing that over and over again until I just memorize it. That was my method. People have so many different ways of doing it, but to me, it was just I memorized it. I thought about it like my times table, and that's the way I would do it. Okay, and Fuzzy Ball said all students take calculus. I think that's always important to remember. So by what they mean by that is all students take calculus is it tells you which values are going to be positive. So for example, in the first quadrant, all the values are going to be positive. In the second quadrant, students, S is for signs, so the signs are positive. Take, T, so that's the tangents are going to be positive. And then the last one, calculus, the only value that is going to be positive here is going to be cosine. Okay, some people say cast. Oh, okay, cast, that's cool. Yeah, there's so many different ways of learning that. It's kind of like when you learn like never eat soggy waffles as north, east, south, and west. Some people say never eat soggy wheat. I believe that's the way people say it. But yeah, there's many different ways of doing that. All right, guys. So let's go ahead and talk about, let's talk about implicit differentiation, implicit differentiation for a bit. I'm sorry. I get so tongue-tied here. Never eat shredded wheat. Yes, thank you, Burner. That's actually the way my wife remembered it, and I always forget it. I always say never eat soggy waffles, but never eat shredded wheat is a great way of remembering north, east, south, and west. Yeah. W wife. Yes, absolutely. She's the best. Okay. So let's talk about implicit differentiation. You're going to see why I'm doing this. Okay. So let's briefly talk about how we can solve something like this. X squared, y squared is equal to 64. We're just going to take the derivative of this. Okay. Yes, implicit differentiation is the one where you put the dy over dx for every y value. So the reason why we're doing this, okay, we're going to take the derivative of this like we normally do. So the derivative of 2x, or the derivative of x squared, is 2x, plus the derivative of y, or y squared, is 2y, but we need to include a dy over dx. So really, I think the best way to remember this is that every time you take the derivative that is not an x, you have to include that dy dx. The reason being is because you're technically doing a chain rule. every time you're taking the derivative. So for example, if we go back to that same problem that we did, okay, when you take the derivative of x squared, it's 2x times the derivative of x, which is 1. Or some people like to put dx over dx, which is the same thing, 1 over 1. So when you're taking the derivative of y squared, it's 2y times the derivative of y, but because this is in terms of x, we need to put a dy dx. And yes, you're absolutely right. I put 64 on the right side, but the derivative of 64 that's on the right side, since that's a constant, that is going to be 0. Berner said, I think it's worth saying why we add dy dx, because some people think it's just a constant in the x world. Yeah, you have to continue taking the derivative of that, but because it's not in the x world, we have to say dy dx. Okay, so this is equal to 0. Now, let's just continue with the problem here. We want to isolate the dy dx, so what we're going to do is subtract the 2x to the other side, and we're left with 2y dy dx is equal to negative 2x, and then divide the 2y to both sides. And we're going to do dy dx is equal to negative x over y. Okay, I'm doing this for a reason, and I'm starting easy so that we can understand this really quickly. Okay, so we said that dx, or x squared plus y squared, if we have this problem, is equal to 64, then dy dx is going to equal to negative x over y. Okay, but now we're going to talk about why I'm talking about this and how this relates to partial derivatives. Okay, so now I'm going to take this function and I'm going to take the partial derivative of this function in terms of x. Okay, and the way this works is that every time we take the derivative of this in terms of x, this is the partial derivative. You're going to treat every other variable like a constant. So what I mean by that is when I take the partial derivative of x squared, that's just literally going to be 2x because that is the variable that we're working with. But when I take the partial derivative of y squared, we don't care about that. It's just a constant. So that's going to be plus 0 and then equal to the derivative of 64, which is just a constant. So that's the derivative of, that's just 0. Okay, so my partial derivative is just going to be 2x. And now let's go ahead and do the partial derivative in terms of y. Okay, so now I'm taking the derivative of this in terms of, or the partial derivative in terms of y. So we're going to treat every variable except the y as a constant. So when I take the partial derivative of x squared, that's considered a constant. We're just going to say that's 0 plus the partial derivative of y squared, that's a y, so that's going to become 2y, equals 0. So then we can say that our partial derivative is equal to 2y. You should check out Leibniz theorem. Okay, bro, send it to me. Or you should let me know in the comments, or one of my comments in the videos, or I'll look it up. I'll look it up myself. Thank you. I keep saying people should send me stuff, but I could just look it up myself. Thank you. I will do. Okay, so I'm doing this for a reason, because now there is a nice little theorem. I think it's called the partial implicit theorem or something like that. But the implicit differentiation of any function is equal to negative the partial derivative of x over the partial derivative in terms of y. And if you recall, we just took the partial derivative, that's 2x, over the partial derivative in terms of y, that's 2y, so, and we had the negative in the front. This cancels out to just negative x over y, which is the exact problem that we had up here. So this is so useful when it comes to taking partial derivatives. I just wanted to bring that up. It seems I lost so many people in the chat. Please, 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 let's not do that again. Maybe we should just go back to integrals. Okay, I have a really nice one that I think we should do. How about this? The integral of secant x. Yeah, Burner, yes, I can kind of agree. You could think of it that way. I think for when it comes to partial derivatives, because I'm seeing a lot of people in the chat are just intern or are just studying Calc 1 and Calc 2. Maybe partial derivatives wasn't a thing that we should even talk about because they're still trying to wrap their heads around just implicit differentiation or just like chain rule type stuff. But I think you're on the right track. Okay, so ln of secant, okay. Yeah, that's an easy one. Taylor for the main audience. Yeah, we can definitely talk about Taylor later on. Okay, so everyone's saying that's just natural log of secant of x tan x. Okay, how about this one? So this is one that I think a lot of us basically just remember. How about this one? Wait, I don't want to do this one. Why is this? Did I write it wrong? Hold on, guys. It shouldn't be that easy. So, yeah, we can do that one. Okay. I don't know why I wrote a problem down and I thought it was something that I definitely wanted to do. But I'm looking at like that's not the one I want. Okay. I lost the integral that I definitely wanted to cover with you guys. I don't even know where it's at. I had it on my notes. I am so sorry. All right. Let's go back to the chat. What do you guys feel like reviewing? Is there anything that you guys have in particular that you'd like to see? Because I messed up on mine. I'm trying to find stuff on my notes. All right, let's see. What can we do? I have a couple integrals that I like to do or that we could do. I have one that requires the Feynman technique, but I still don't see how I can get to it. Okay. Let's see. Excuse me for a second as I move along. Okay, so let's go ahead and try to solve. Let's just kind of start off with an easy one so far. Okay, I have this one that I keep writing down. I don't know why. I don't think I covered it in my previous lives. I think hyperbolics are taught. Gosh, I don't even know. For the most part, college. I think sometimes they introduce it in high school, but definitely college. I think in high school they just kind of go over the basic functions. So I would say college. What about you guys? All right. How do you guys suggest we solve this problem, by the way? What do you think? Any specific methods in mind? Okay, well, let's go ahead and try U sub. 17 through 18. Yeah, to be honest, man, America is way behind. I see people messaging me like, you should look at, these specific things in other countries, and it's just insane. So shout out to you guys. We are way behind. Oi said U sub, yes. So U is equal to root x dx. And so that means that du is equal to 1 over 2 root x dx. And up on top, I say u is equal to root x dx. So I think it's just u is equal to root x. Okay. So again, as I like to do is I like to leave this over here. Okay. I like to multiply the 2 root x to the other side. I think it's much cleaner in my opinion. So 2 root x du is equal to dx. And so when I plug that back into my integral, this is what I get. I get cosine of u times 2 root x du. There's a problem here. Our integral was now in the u universe, but I still have that root x. So what do? What do I do with that root x that we have here? Fuzzy Ball said, let's go ahead and replace u. Yes, I 100% agree. So we're gonna look at the integral that we have up here. U is equal to root x. Okay, so then now we can say that integral of cosine of u times du. And then someone said rearrange it. So Bernard, I'm just going to rearrange it again. 2u cosine of u du. And now we can do u sub again, or in this case, I believe it's going to be an integration by parts problem. So we're going to make u equal to, let's do 2u. du is equal to 2 du. dv is equal to cosine u. And then v is equal to sine u. Okay, I realize it's a little weird because I use u twice again. I guess I should have done like w or something. Let me change that. So instead of u, I could have done like dw and then dw. All right, so let me go ahead and make some space on the blackboard, and then we can talk about other methods after that. Let's see, where is my, there it is. Trying to look for the specific cursor on my screen here. All right, so now what we're left with is 2u sine of u minus sine of u times 2 du. Let me rearrange this. So minus, I'll just put the 2 on the outside, sine of u du. And luckily for us, we can easily integrate this and do 2u sine of u minus, this is going to be plus 2 cosine of u and then plus c. Yes, tabular method for sure. And now what we can do is, since our u was equal to root x, we can do 2 root x sine of root x plus 2 cosine of root x plus c. There we go, guys. Yeah, I can see that. It's like when people use like I in summations. A lot of people get really mad about the summations here. Like if I use like this summation, I is equal to 1 to infinity, a lot of people would say that the I is a complex. So I can see that. People get very picky with those types of problems, that's for sure. Okay. If no one has a problem yet, I'm going to pull one that, where did I see this? I'm trying to find it's on my phone, but I'm going to try to find a specific problem where we have to use the Feynman technique, because I think that is the most complicated and most frustrating thing that I've been working with in a while. I don't know why. Okay, so let me just go ahead and pull out a problem real quick. We're going to do this together, guys. Okay. It's funny, every time I look up the Feynman technique, it's like Feynman technique for learning, but we just want integral. So I guess we want Feynman integrals. Okay. All right. So let's see if we can make sense of any Feynman integral here. Okay, this is the one that I just did. Okay, let's try to do another one. Okay. Again, this is the one where I don't understand it. I'm just going to write it real quick. This is going to be integral from 0 to pi of e to the cosine of x, cosine of sine of x dx. Yeah, see, I tried the Feynman technique too, and it doesn't make sense. Okay, but we're going to try this out. So I've been looking at this online, and I tried it, and if someone sees a mistake, please let me know, because I just can't. Okay. So let's go ahead and try this out. Apparently, if we're going to use the Feynman technique, we're going to make our f of k equal to 0 to pi of e to the k cosine x times cosine of k sine x dx. Okay, so that was the clue that they gave me. Again, this is I would say a paper that I read or that I was reading online, and I just don't understand it. It makes no sense to me. So, according to the Feynman technique here, we're going to go ahead and take the derivative. And I guess since both of these values have k, I have to use the product rule. So it's going to be e to the k cosine x times sine k sine x times, and then this is just going to be sine x since it's a partial derivative, and then plus cosine x e to the k cosine x cosine of k sine x dx. That's what they're telling me, or that's what I'm trying, and it just doesn't work. Okay. So let's see what I could do. Again, this is a right? I don't know. I mean, again, we're going to try this. So let me just try to clean this up a little bit. I mean, let me just try to make it smaller. So maybe I can zoom in on my iPad real quick. You guys are going to see why I'm doing this. So f prime of k is equal to integral of 0 to pi of, let's put the ek cosine x, and let's put the sine out in the front, and then times sine of k sine of x, and then plus, I guess that's kind of already cleaned up. I'm just going to do e cosine of x times cosine of x cosine of k sine of x dx. Okay, Burner Sir, wait, am I missing something? I hope I'm not. We'll see. Yeah, see, what differential equation are we talking about here? I think you're right, but I don't know what differential equation this will be. Definitely going to split into 2. So let's go ahead and do that now. So this is going to be f prime of k is equal to, let me just ask, so we don't miss anything. Sine of x times sine of k sine of x dx plus integral from 0 to pi of, and then the other function, e to the k cosine x cosine x of cosine k sine of x dx. And then factor out cosine from both or just the first one? And then factor out cosine x from the second one. Okay. So this is from the second one. I mean, again, we're going to try this. So supposedly, this is going to be plus integral. So this is just a second function. So I'm going to factor out the cosine. And this is e to the k cosine x cosine k sine x dx. Bro, and then you're saying that this is the original function. This is the original function f of x. Yeah, see, we can't factor it out of the integral, unfortunately, because then that will make it, because it's in terms of x. Yeah, you see? Bro, this is where I get stuck. So I don't know. Let's try. Okay, so then I guess that won't work because we thought we had something, but that's the whole point of doing this stuff. So let me just erase this. Is it possible? Can I even do like u sub in some way? Like for the first integral, I was maybe thinking u is equal to cosine, and there's our du technically, but then you're still left with all that. Yeah, exactly. So this is, again, this is the problem that they have in terms of that. You guys, someone should write this down and try to work it out because I'm trying and for the life of me, I just can't get it. Okay, but I have another one that we can do together and see if I feel like I got it, but I just did not understand what was going on. Okay, so let me just go ahead and erase this. Okay, someone take a screenshot if you need to, but try to do this on your own. But I'm going to try another one using the Feynman technique because I feel like I got close to this one, but I just couldn't get it. All right, so I'm just going to go ahead and erase it, and we're going to work this one out. Let me go ahead and write this down. Whoops, it doesn't look like it's going to let me. So there we go. I have to clear it on my computer. Okay, so this is the integral 0 to 1 of natural log of x minus 1 over x squared plus 1. Now, this is very similar to the very first integral I did. Yes, Burner, please play around with it, because this is just like it was making my head hurt and annoying me. Okay. So according to the hint, they're saying to make your f of k equal to 0 to 1 of natural log of kx minus 1 over x squared plus 1 dx. And so if we take the derivative of this, we're going to treat the x squared like a constant, and we're just going to do 1 over kx minus 1 times x dx. That's what they told me, at least. Let me make sure that I actually have that right. Again, it's so frustrating that I can't get this. I wish I could. Okay, so let me just rewrite this again. If I get anything correct, please let me know. So this becomes, I can technically do kx minus 1 times x squared plus 1, and this is just x dx. Yeah, so I took the partial in terms of k. So I did 1. Yeah, I think I did that correct, because I took the derivative of that. Okay, so this is what I'm left with. X over kx minus 1 over x squared plus 1. And we're supposed to integrate this. And I'm assuming that we do partial fractions. I'm assuming that I can rewrite this as a over kx minus 1 plus bx plus c over x squared plus 1. What do you guys think? Yeah, we can make our own theorem. I mean, it's so difficult. You plug in this is insane. I wouldn't know how to solve this. Okay, but I'm just going to try the partial fractions here. Okay? If you guys have any suggestions, or if you guys have a specific integral you guys want to solve, then let's run with it. But this is just frustrating me. I just cannot believe that I can't get that. But if I use partial fractions here, this will mean that a times x squared plus 1 plus bx plus c times kx minus 1 is equal to just x. Okay, so let's distribute the a. So this is ax squared plus a plus, I have to FOIL the next part, bkx squared minus bx plus ckx minus c is equal to x. Okay, so I'm just going to go ahead and try to combine all this stuff. So a plus bk times x squared plus, let's see, those are all my x squareds that I combined. And then I have negative b plus ckx plus a minus c is equal to x. Okay, let's make this a little smaller. This is just insane, guys. This Feynman technique just is killing me. Whoops. Okay, here we go. So this tells me, if we try to match it to the right side, this tells me that a plus bk is equal to 0. Negative b plus ck is equal to 1. And then a minus c is equal to 0. So then a is equal to c, which I think can prove helpful, because I can plug it into the equation on this side. And so I have c plus bk is equal to 0. And then if I combine it with the second equation, I can do ck minus b is equal to 0. And I guess I could introduce a negative k to that top equation. And then I'm left with negative ck plus bk squared is equal to 0 over ck minus b is equal to 0. And I can combine these things. Oh, this was equal to 1. Hold on, this was equal to 1 over here. This is how confusing this can get, guys. So then I am left with negative b k squared minus b is equal to 1. So if I factor out a negative b, I get k squared plus 1 is equal to 1. So b is equal to negative 1 over k squared plus 1. Well, that gives us something in terms of k. And now we just got to figure out what c is equal to, and then that'll tell us a. Okay, well, I think that helps in some capacity. Let me show some work here on, I'm just going to show some work on top. So if we know that b is equal to negative 1 over k squared plus 1, and we know that negative b plus ck is equal to 1, so then ck is equal to 1 plus b, ck is equal to 1 minus 1 over k squared plus 1, and then if I divide the k to the other side, c is equal to 1 over k minus 1 over k times k squared plus 1. Yo, this is just crazy. Positive bk squared. Someone said positive bk squared. Where was a positive bk squared, Bernard? Do you see that? Do we see where that is? The positive bk squared. I'm trying to make sense of where that would be. Oh, I see it. I see, because I was supposed to multiply by negative bk minus b, negative k. If you add the two equations, it will be bk squared, not negative. Are you talking about the problem that I have up on top? If you add the two equations, it will be bk squared, not negative. I'm trying to see what that is. Bk squared. Negative 1 over. Oh, the system. So let's see. I had negative c plus bk is equal to 0. Oh, bk squared. And then I had ck. Well, so it should be negative b squared. And then minus plus ck. Oh, no, minus b is equal to 1. And I think if I'm supposed to add these together, so it should be negative b k squared minus b is equal to 1. So negative b is equal to k squared plus 1 is equal to 1. I think it should be, why do I keep getting a minus bk squared? Because a was equal to c. Because I multiplied. Okay, you're messing. Okay. All right, just making sure. All right, so let's go back to the c, what we were trying to solve for that. I'm just going to double check our work. C is equal to, I got to get common denominator. So it should be k squared minus 1 over k times k squared plus 1. Keep in mind, this is just k. It's supposed to be a constant. So that's kind of nice. So the 1's cancel out up on top. So then we're left with c is equal to k squared over k times k squared minus 1. And then one of the k's canceled out. So k over k squared minus 1. So keep in mind, we have b. Up on top, we have c. And technically, that's also equal to a. Yo, we haven't even finished what this integral is supposed to be. But it looks like now we set it up correctly. So now let me go ahead and make things smaller. And I think now I'm going to be able to write our entire integral. So that now we can do integral from 0 to 1 of x over kx minus 1 times k squared plus 1 dx is equal to, and then we had said that it is a over k plus 1. So a is k over k squared minus 1 times kx minus 1. But these are all constants, thankfully. And then plus b is negative, so it's negative 1 over k squared plus 1 x plus our c, which is still k over k squared minus 1, all over k x squared plus 1. But these are all constants, so we're not going to really care too much about it. So this is all the integral in terms of dx. Your C value and your A value should be k squared minus 1. Oh, yeah. It should be k. You're right. Plus ones. Yeah. Okay, so then my A is over here, and then everything should be k squared plus 1. Let's go. Yeah. Oh, hey, Rio, and hey, Stella. Welcome. All right, guys, so let's continue. We still need to integrate this entire thing. I'll add my parameters at the end. Stella, Vivian, Rio, what's up? Everyone say hello to Stella, Vivian, Rio. They are the dynamic trio. Okay, let's continue. For that first integral, actually, let me color code it so that we don't lose track of this. Okay. Yes, it is very hard. Okay, so let's go ahead and do the red one first. I'm just focused on the red. I'm going to pull out all those constants. And that's going to be k over k squared plus 1, and then integral of dx over kx minus 1. I feel like that's a simple natural log problem. Plus, now let's focus on this one. So we're going to pull out the minus k squared, so maybe I can just do that. Oops. So now we're going to do minus 1 over k squared plus 1 integral of x over x squared plus 1 dx. And then the last one is this one. And I believe that was a k squared because that was a plus, that was a c value. So then it should be 1 over k squared plus 1 integral of 1 over x squared plus 1 dx. Yeah. All right, guys, I feel like we're almost at the promised land. This is going to be insane. Let's go ahead and finish this off. Again, the first integral in red looks very simple. I think it's just a natural log. The second one is arctan. No, it's a u sub, and then that second one is an arctan. Oh my gosh, I think we're going to get this. So this is going to be, I'm getting so excited about this. Correct me if I'm wrong, but I'm just going to kind of do this in my head. For the red one, I'm going to do a u sub. So this is going to be k over k squared plus 1 times 1 over k natural log of kx minus 1. Okay. Oh, trust me, it'll be on my YouTube for us to look at. This was such a train wreck, but it's been fun. You guys are making it worthwhile. All right. So this next one is going to be 1 over k squared plus 1 times 1/2 natural log of x squared plus 1. That was just a u sub. And then we got the last one in blue. Guys, plus 1 over k squared plus 1 arctan of x. And this has all the parameters from 0 to 1. Oh my goodness. We're about to get this Feynman technique. Jeez. Okay, let me make this even smaller. I think we are on the right track, guys. Now we just got to plug in the 1. We got to plug in the 0, and I think this is going to work. Okay, so we're going to plug in the 1 into the first part, and we're just going to plug in x into it. Or we're going to plug it into the x. So the first part is k over k squared plus 1, I guess, times 1 over k. We'll worry about the k's in a second. Natural log of k minus 1. And then minus 1 over k squared plus 1. We'll worry about the 1/2 in a second. So we'll do times 1/2 natural log of 2. And then plus 1 over k squared plus 1. And then arctan of 1, which that's just going to be pi over 4. And then I believe when you plug in the 0, all that's going to go away. So when you plug it into the natural log, that goes away. When you plug it into this natural log, that goes away. It's just 0. And arctan of 0 is just 0. Holy shit, guys. We got it. We got it. Okay. Let me just kind of make this a little smaller. Okay, so this tells me, I know this is a lot of work, that the integral from 0 to 1 of natural log of kx minus 1 over, shoot, what was the integral? I think it was x squared plus 1. Over x squared plus 1 dx, or this is our f. Yeah, we took the integral of this. Oh, this is our f prime, is equal to this whole thing. So now let's simplify. This is natural log of k minus 1 over k squared plus 1 minus 1 over 2 k squared plus 1 natural log of 2, and then plus 1 over k squared plus 1 pi over 4. Is this our f? Is this our f of our fk or our f prime? Because we integrated this whole thing, right? Or do we still have to take everything in terms of k? This is a k squared. Oh, man. Wait, I still think... Now, no, that would have been where you took partial. Wait, no, it is x squared, right? Hold on, let me... Or it's k squared. No, it's k squared, right? That bottom one, it should be k natural log of... Oh, it should just be k minus 1. So this part should just be... This part should just be a k minus 1. And then this bottom one, I think it's just a k squared. It's not an x squared. Yo. This is insane. Okay, so this is as far as I can possibly go, because that's still our derivative. Oh, no, that's an x squared. You're right, because I took the integral. Burner, you are 100% correct. Yes, so let me just rewrite this. F prime of alpha is equal to, we said the integral of... No, we haven't even taken the integral. So our f prime of alpha, which was the integral that we took, was this whole thing. Ln of k minus 1, no, you're right, is equal to k squared plus 1. I just wrote the integral on there. Minus 1 over 2 k squared plus 1 natural log of 2 plus pi over 4 arctan. No, not arctan. I'm already thinking way ahead. This is just pi over 4 times 1 over k squared plus 1. So all we have to do is integrate this in terms of k. But then that first one... Okay, this is where I get stuck. Okay. So we're almost there. We're almost there. Okay, and then after this, you guys can all go and be as confused as I am, but I'm going to make this just a tiny bit smaller. So again, this is where I keep getting stuck. I'm going to take the integral of everything here. So this is just f of k. We were using k, now alpha. F of k is equal to the integral of natural log of k minus 1 over k squared plus 1, which I think it's almost the same integral, plus this is going to be natural log of 2 over 2 integral of 1 over k squared plus 1 dk, and then plus pi over 4 integral of 1 over k squared plus 1 dk. Y'all see that? I just have to take all we have to do is take the integral of this. So the first one, if we go even smaller, God, this is like the matrix. The matrix can't get us. So now this whole thing is equal to, I don't know what this integral is. This is where I get stuck. This is plus natural log of 2 over 2 arctan of k plus pi over 4 arctan of k. Yo. And this is where I leave off. I don't know what to do with this. So take a screenshot of this, guys. Try to practice with this and try to mess around with it. This is literally just me trying to understand it myself. I don't know how to arrive at the answer. Just a heads up, apparently the answer is pi over 8. That's what I saw online. So we'll try to do that. Okay? Today was basically an off-trail session. It wasn't supposed to have a specific agenda, but I hope you guys had fun. This is insane. I still don't know how to work the Feynman technique, but I'm hoping that we can do this together. Okay, I'm going to catch you guys on Tuesday. Tuesday is going to be integration B, so we're just going to do a bunch of integration problems, hopefully techniques that you guys all are familiar with, and we'll mess around then. So hopefully around this time works for you guys on Tuesday afternoon. I'm going to try to do another one earlier on Monday night and maybe Tuesday night. I'm going to have some extra time. But yeah, guys, until then, I hope you guys enjoy the weekend. I am going to have some delicious vegan sushi today. Hopefully a nice, some wine and just chill. All right. Well, I hope everyone, again, has a good one. Take it easy. Be safe out there. And don't get into any trouble, please. All right. Ta-ta. Until next time.